Welcome back. So today we shall continue our circular motion. So now, the last class I stopped at explanation of proving centripetal acceleration. Of course, um, we all know that centripetal acceleration is mv square over radius, where m is the mass, v is the velocity, and r is the radius. So each centripetal acceleration is this. We call that the length of an arc. The formula is radius multiplied by angular displacement. Now check this diagram. Check this object A. Object A, the object was formerly at A, now at B. It changes direction. I remember that any object or particle undergoing circular motion, the direction of velocity is always tangential. Look at the way I drew it. It's always tangential to the circle and perpendicular to the radius. Perpendicular to the radius. So the fact that the object was formerly at A, now at B, is being displaced. That's angular displacement, not linear displacement. It displays in a curved path, not linear. That's why we have theta here. So the distance covered from A to B is an arc. So the length of an arc, the formula is r multiplied by theta. So if s is equal to r theta, let's divide both sides. Let's divide both sides by time. So we have s over t equal to r theta over t. So displacement over time will give us velocity, and this is this. Remember from our earlier definition that angular displacement divided by time will give us angular speed or angular. So therefore velocity is equal to Rw. If velocity is this, then centripetal acceleration can also be written as this: m over r multiplied by v squared, where v is Rw. Remember there's the square there. So centripetal acceleration can be mr squared w squared divided by r. So radius cancel this. So therefore centripetal acceleration can also be mrw squared. So the formula for centripetal acceleration based on the parameter given in the question can be mv squared over r or mrw squared. That's for centripetal acceleration. Now let's move to centripetal force. Let's move to centripetal force. Let's move to centripetal force. Now, for centripetal force, centripetal force F is the force required to keep an object of mass moving in a circle of radius r. Let me put it down. The force required to keep an object. The force required to keep an object of mass m, can be an object or a particle of mass m moving in a circle of radius r. That's centripetal acceleration. The force required to maintain an object moving in a circular motion. So for an object to be in circular motion, there must be centripetal force that keep the body or object in circular motion. It's always directed toward the center of the circle. Yeah, since F equal to ma. So when we are talking about for centripetal acceleration, centripetal force, the acceleration also must be centripetal. So centripetal force Fc is centripetal acceleration is v squared over r, or centripetal acceleration can be r can be m r w squared. So therefore centripetal force can be mv squared over r, or mr w squared. That's centripetal acceleration. The force required to maintain an object in a circular motion, which is always directed toward the center of the circle, is called centripetal acceleration. Now, let's see the application of centripetal. The application of centripetal acceleration. Number one, we're going to analyze it one by one, or let me call it case one. Now, case one is this: when a stone is y round a circular path. Round a circular path. When the stone is y round a circular path, horizontal circle to be precise, horizontal circle, by means of a string, Now, when a stone is y round a circle, in horizontal circle by means of a string, the tension provide the centripetal force. How? Let's see it. The tension provide the centripetal force. Let's see how. Like I said the tension provide the centripetal force. Remember, centripetal force is always acting toward the center. Now, this is a circle. Now, this is you holding whiling a circle, whiling a stone round a circle. This is the stone. You know, the way you while in such a way that the only way the force in the tension, the force in the rope is tension. The only way to maintain this stone around the circle is to while it round toward yourself. As I mean, just imagine you're whiling toward yourself. That's the only way the stone can be maintained in a circle. And there's some analysis, or there are some common questions the syllabus expect us to know. For example, this is one of it. The syllabus usually asks some analysis when the stone is at the top and when the stone is at the bottom. The syllabus wants us to understand what is going on at that instant. Remember that let me talk about the top now. There's a tension attached to the stone toward the center. At the same time, the weight of the stone is acting downward. The weight of the stone is acting downward. Remember that the essence of this is to make sure the stone is moving toward the center. So we have two forces now. Weight is measured in Newton, tension is measured in Newton. They are acting downward. This is the logic. Remember your Cartesian. Up is positive, down is negative. So if you relate it, you see that the weight and the tension, they are in the negative region. So which means minus weight minus tension. The essence of this is to give us centripetal force. We give us centripetal force. And mathematically, minus 2 minus 3 should give you minus 5, right? So minus weight minus tension will give you minus the answer. So from here, we can factorize the minus. We have weight plus tension equal to minus centripetal force. Minus cancel minus. So the weight is mg plus the tension. Centripetal force is mass times centripetal acceleration. So we have mg plus tension equal to centripetal acceleration is v squared over r. So from here, so we have tension at the top. Tension at the top will be mv squared over r minus mg, to which is the same thing as m into bracket v squared over r minus g. This is the tension at the top. Now, there is another concept in such a way that it might be hard to find the minimum velocity to keep the stone in motion. Obviously, tension cannot be less than zero. Tension cannot be less than zero. So the minimum tension to keep the stone in the circle will be zero. So in this case, we can since tension equal m into bracket v squared over r minus g. So the minimum velocity to keep the particle or the stone in motion, then put t to be zero at that point. So we have m v squared over r minus g equal to 0. At the end of the day, v squared over r minus g will be equal to 0 when you divide both sides by m. So v squared over r equal to what? G. So that minimum velocity occur when g is v squared over r. So therefore, v squared will be equal to rg. So the minimum velocity to keep the object in circular motion is square root of rg. Now, another case is when the stone is at the bottom, or when the particle is at the bottom. If you consider the top, so when the particle, after whiling it, is now at the bottom. Okay, obviously the weight is downward. The weight will be downward. The tension is toward the center. This is the person whiling it. That's the tension toward. So now, of course, acceleration will be toward the center. The whole essence to keep the particle in circular motion is it must be directed toward the center. This is acceleration toward the center. So after drawing a Cartesian, up is positive, down is what? Negative. So in this part, so the resultant force will be positive tension minus weight. In this case, the resultant force will be that. So, of course, the tension will be greater than weight. Newton's second law, resultant force is mass times centripetal acceleration equal to tension minus weight. Centripetal acceleration is v squared over r equal to tension minus weight. Weight is mg. So in this scenario, tension in this scenario will be m into bracket v squared over r plus g. This is the tension at the bottom. Tension at the bottom of the circle. So the syllabus expects you to know what is going on at the top and also at the bottom. That's it. Let's move to another case. Now another case, um, let me call it case 2. Now case 2 is like the roller coaster theme park. You know, in case 2, consider object consider the object moving inside. It's like the way roller coaster I found. Consider the object moving inside the circle, you know, going like this. The object is moving inside the circle. So point A, I need to know what is going on in point A and point B. This is inside the circle. There is no tension. There's no tension to while you are around. It's like an engine moving it inside the circle. No tension in this case. No tension attached to the object. Now, okay, the first thing you're going to observe is that the weight at A, okay, at A, the weight is vertically downward, of course. The weight is vertically up downward. Now, this part of the circle is exerting a force, a normal force. You know, it's called contact force. There's a contact between the object and the circle. So in this case, is there's a contact force on the object. The contact force is called reaction force. So, and again, it's also accelerating downward. It's toward the center. This acceleration toward the center. So let's analyze what is going on at A. Now, when you draw your Cartesian, like I said earlier, up positive, down negative. The two forces in question, the weight in this case, the two forces in this case is weight and normal reaction force. They are downward. So that will be normal reaction force minus the weight. Of course, minus will give us minus answer. So the resultant force in this case is also centripetal force. When you factorize your minus, so what do you have? Reaction, normal reaction, let me just call it R, the normal reaction. Let me just call it R. Let me call it R, normal reaction. Let me just call it R. So the normal reaction at the top, let me use T. When you factorize, we have this minus centripetal force, you all know, is mv squared over R. Minus cancel minus. So at the end of the day, the normal reaction at the top plus weight equal mv squared over R. So what do you have here? So our normal reaction. The question might ask you to find the reaction force at the top. The reaction force at the top will be m is common, v squared over R minus weight. Weight is mg. So this is the normal reaction at the top. It's also similar to when tension is holding it. So this is the normal reaction at the top. Now, let's see the normal reaction at the bottom. Let me use another color. At the bottom, of course, the weight is acting downward. Now, the contact force on the object now in this case is upward. Of course, acceleration is toward the center of the circle. So for the bottom, so this is what we have for the bottom. We have to, the normal reaction is negative is upward, sorry, positive, weight is negative. And in this case, the resultant force will be plus R minus weight. So, and resultant force is mass times acceleration. Reaction at the bottom minus the weight mg. Mass times acceleration is mv squared. You know, since the acceleration 2 is, when you check this, acceleration is also upward, it's on the positive part. So that's the reason why ma is positive and centripetal force will be positive. mv squared over r equal to reaction force. At the end of the day, reaction at the bottom will be m into bracket v squared over r plus g. That will be the reaction at the bottom. M into bracket v squared over r plus g. Now, there are some things you should know now for this reaction. Okay, at the bottom, NB, let me start from the top. At the top, there's something you all should take note at the top. At the top of the ride, the weight and the normal force both act toward the center. I've already said that the weight and the normal force both act toward the center. So, which means that the centripetal force at the top, centripetal force will be greater than the weight. Centripetal force will be greater than the weight. If you check it at the top, centripetal force will be greater than the weight. And reaction at the top from the seat, the reaction at the top, the reaction at the top, the reaction at the top from the seat, is less than reaction at the bottom. You should note that it's less than reaction at the bottom. Reaction at the top is less than. If you see the reaction at the top is in the negative region, reaction at the bottom is in the positive region. So reaction at the top is less than reaction at the bottom. Take note of that. And also, if B is not large, then the top of the circle, the weight may be greater than the centripetal force, and the person will lose contact and fall inward. You should take note of that also. Now, let's see another case. Case C. This one came out this year, paper 4 variance 1, 2023, May, June. Something like this came out. They started setting some questions. Yeah, they want to test your application on how you understand circular motion. So case C. Now, case C is like conical pendulum. Conical pendulum look like this. The case is like whirling a stone around a circle at a particular angle. Okay, let me use another color for this. This is a stone. Now the stone is attached. The stone is like this. The stone, you are whirling a stone at a particular angle. So tension, something like this. Whirling the stone at a particular angle, theta. Okay. So now, this is the center, 0. And this is where your hand is. This is where the hand of the person whirling it is. Now in this case, now this is the center of the circle. This is the center of the circle. Let me call it B. Now, the particle will exert a weight downward here. The weight is mg. From the particle to the center of the circle, that will be the radius. Of course, you are aware. Now, the tension force, the way you are whiling the stone is not straight, it's at a particular angle. In physics, when you are given a force at a particular angle, what do you normally do? We resolve. So this is the tension like this, and this is the angle. I need to resolve vertically and horizontal. This is vertical, this is horizontal. Vertical, that will be adjacent over hypotenuse equal to cos theta. I'm resolving t. So when we resolve t vertically in this context, I have t cos theta. If I resolve t vertically, it's t cos theta. Let me resolve it horizontally. That's sine theta equal to opposite over hypotenuse. If we resolve t horizontally, I have t sine theta. Horizontally, I have t sine theta. You take note of that. So now, let's continue our work. So from here, so what you expect to do, what they expect us to know is this. Now from here, now vertical, since there is no motion vertically or vertically, there is no motion or there is no motion vertically, which means the vertical forces counterbalance each other. There is no motion vertically, which means the vertical forces counterbalance each other. The vertical force is t cos theta and mg. So t cos theta should be equal to mg. T cos theta is equal to mg because there is no motion vertically. And again, circular motion, is always tending toward the center of the circle. So in this case, what gives us centripetal force? What gives us centripetal force is T sine theta in this case. T sine theta provide centripetal force. That's the horizontal motion. So now resolving, so T cos theta equal to mg, T sine theta equal to mv squared. So let's divide equation 2 by equation 1. So equation 2 is T sine theta. Equation 1 is T cos theta. Equation 2, mv squared over r divided by mg. That will be times 1 over mg. So T cancel T, sine theta over cos theta will give us tan theta. M cancel M. What do you have? V squared over rg. So that's the relationship. So that's the relationship for conical pendulum. We are still going to solve the past paper, how to apply this T cos T sine theta over this. And there are some algebra analysis we can play with here. So anyway, when we get to that part, we're going to cross it. This is case C. I hope it's clear. Now, let's see another case. So let's see this case D. An upside down bucket. Upside down bucket. Now, an upside down bucket is like a roller coaster. So let me just put this note. For the same reason that and upside down for the same reason that upside down roller coaster, for the same reason that an upside down roller coaster won't fall. You know, imagine an upside down roller coaster won't fall off the track, won't fall off the track. Comma. Water, upside down water too, won't fall out, won't fall out of, won't fall out, won't fall out of an upside down, won't fall out of an upside down, upside down bucket if it's moving in a circular motion. If it's moving in a circular motion as fast enough, as fast enough velocity. Anyway, now this is an upside down. This is a curved part. This is the bucket. This is the bucket. An upside down bucket. Now, of course, we have the normal reaction is down, and of course, the weight is also down. Acceleration is also down. So in this case, our resultant force, that's minus weight minus normal reaction, will give us minus centripetal force. When you factorize, like we did earlier, we're going to have this normal reaction. So centripetal force is mv squared over r. Weight is Fg plus normal reaction. So normal reaction will be m into bracket v squared over r minus g. Now, for safe speed, the normal reaction will be greater than or equal to 0. So if normal reaction, the minimum is 0, so we have v squared over r minus g will be equal to 0. So v will be equal to gr. So this is the speed, provided that the bucket is moving with this speed. The water is not going to fall out of the bucket. As long as the bucket move with this velocity, the water stay in the bucket upside down. Let's see the last case. The last case is banking. When a vehicle or a car is moving in a curved path. Normally, this is how a vehicle moves straight. Normally, to move straight, this is a normal reaction, and this is the weight, and this is the road. The vehicle is always moving straight. Now, and the frictional force between the tire of the vehicle and the road. Now, when the vehicle is now banking means going in a curved path. when the vehicle is now banking. Look at the vehicle now in this case. It's going in a curved path, it's banking. You can see the vehicle is now banking. Of course, the frictional force, banking means going in a curved path. There will be frictional force. The frictional force will be opposite the motion. So this is the frictional force opposite the motion. Now, this is the weight. This is the weight of the vehicle. Now, what do you notice now? You see that the normal reaction has shift position. The normal reaction that was, look at in A, normal reaction was straight. Now, look at the normal reaction now. It has shifted by a particular angle, theta. Like I said, in physics, when you have forces, a force that is moving or that is bent at a particular angle, you need to resolve. So let's resolve the normal reaction. This is normal reaction. We need to resolve it vertically and also what? Horizontally. This is the angle. So to resolve it vertically, that's adjacent over hypotenuse. That's cos theta. So vertical force of normal reaction is okay. My normal reaction n is also the same thing as Rn anyway. Is n cos theta. Horizontal force, so here is n cos theta. Vertical horizontal force sin theta x over n. So when you resolve the normal reaction horizontally, we have n sin theta. So this side is n sin theta. So in this context now our vertical force, vertical normal reaction now is now normal, n sin theta. Horizontal is now, vertical is n cos theta. Vertical is n cos theta. Vertical is n cos theta. So n cos theta. Horizontal is n sin theta. So now we check the diagram. N cos theta will equal to mg, and n sin theta. So the next term will be n sin theta is one that provides centripetal force based on the assumption that friction is not necessary. Friction is zero in this case. So this equation 2. We can also divide equation 1 by equation 2. Equation 2 by equation 1. So we have tan theta equal to mv squared over r times 1 over mg. M cancel m. So v squared will be rg tan theta. In this case, v is square root of rg tan theta. There are a lot of questions they can ask based on this diagram. So this is the end of what is required from the syllabus for CIE, circular motion. So my next class will be solving past paper. I believe I'm going to solve like 4 questions. This year question, 2021 October, November, and 3 or 4 questions. So to perfect what we've learned so far. So see you in the next class, gravitational force of attraction. Subscribe and share. Thanks.